Okay, here is the last little bit, 41 through 40, whatever. Okay, N2 molecules absorb ultraviolet light, but not visible light. I2 molecules absorb both visible and ultraviolet light. Which of the following statements explains the observation? Um, Here's the thing that's crazy about this is the only thing that they want you to know is in AP chemistry is about these shells. So like nitrogen. I'm not going to do the whole thing, but nitrogen is 1s2, 2s2, 2p3, because 2 plus 2 plus 3 is 7. And so it has, in the first energy level, there's 2 electrons, and in the second energy level, there's 5 electrons. And the only thing, this is chemistry, it's not physics. So what happens is when we zap an atom with ultraviolet radiation, we do one of two things. We get the electrons, okay, and keep in mind there's an n equals 3 out here and an n equals 4 that are empty. We can zap electrons so that they jump up to empty energy levels, and then when they jump back down, they release energy. You remember way back last year we had spectrums with little flashes of color. And so it's chemistry. This is about when you shoot energy at an atom, you either make the electrons jump around and they absorb and release energy based on how they're jumping between levels, or you knock them out, and that's what a PES is. But this chemistry is all about how does energy interact with an atom, because electrons have energy based on what shell they're in. So, okay, so then it says nitrogen molecules absorb ultraviolet light, which means when you shoot ultraviolet light in them, the way they absorb it is they absorb energy, and that gives the electrons enough energy to jump to empty um, unoccupied shells. They're jumping around between orbitals. And then I has molecules, which has a lot more electrons, it has a lot more shells, absorb both visible and ultraviolet light. Which of the following explains the observations? And the only answer that makes sense, because it absorbs energy, it's absorbing energy. That means it's absorbing energy to make the electrons jump up. Visible light does not produce transition between electronic energy levels in the N2 molecule, but does produce transitions in the I2 molecules. Basically, we're not removing an electron from an atom. Okay, it's just absorbing energy, and the absorbing energy is making the electrons jump up. And it's not about vibration. There is something called, God, what is that called? In organic chemistry, you do some of that vibrational stuff, but it is not part of the AP chemistry curriculum. It's all about, by the way, I did atoms, but N2 molecule is just 2 nitrogen molecules hooked together. All right, enough said about that one. Okay, this is crazy. This is alloys. And what you got to understand is this is a question about metallic bonding. And metallic bonding is the weirdest of all the bonding, because and this was a long time ago, we explain this in terms of the electron C model. And what happens is when you crowd a whole bunch of like iron atoms together, they participate in metallic bonding. And so what happens is each iron atom gives away 6 electrons and turns into a little tiny, much smaller iron cation with a +6 charge. You can't even see that. And then 6 electrons per atom go into the C, and these start flowing. And what happens is this island has a +6 charge, and the electrons in the C have a -6 charge. And that, according to Coulomb's law, is a huge, huge force of attraction, because of the Q positive, the magnitude of the positive charge, and the magnitude of the negative charge. This is 6 times 6 is 36. I mean, metallic bonding is the second strongest diamonds, covalent network solids. And so what happens is then we found out that if we alloy the metals, you can make them even stronger. For instance, steel is stronger than pure iron. And the reason is the little tiny carbon atoms can fit in these gaps, and then they can add even more electrons in the C, and they make the force even stronger. So this question is saying, to make gold stronger and harder, it is often alloyed with other metals such as copper and silver. Consider two alloys, one of copper or gold and copper, and one of gold and silver, each with the same mole fraction of gold. If the AuCu, so if the gold copper alloy is harder than the gold silver alloy, which of the following is the best explanation? Okay, so they're asking us, and then they give you information about the size. So notice copper is smaller than silver. Notice copper has a higher melting point than silver. And then oxidation state. I just think that stuff is distracting. Which of the following is the best explanation for the iron copper alloy being harder? Harder means the bond is stronger, the metallic bond. Copper has two oxidation states, but silver only has one. That has nothing to do with it. Okay, that has to do with forming compounds. This is why is it when you put copper atoms and silver atoms and gold atoms together, what's going on there? Copper has a melting point? No, because we're making it harder, and harder doesn't have to do with phase change. It has to do with like, it's not easy done. Copper atoms are smaller. I would agree, that's true. Can you see that? Thus, they interfere more with the displacement of atoms in the alloy. That is the answer, because it's this idea of this interstitial alloy, and the most important interstitial alloy is steel, where it's smaller and it gets in there. And then I would not, copper atoms are less polarizable. That's true because they have less electrons. But interparticle or intermolecular forces, they aren't about ionic bonds and covalent bonds and metallic bonds. They're about phases and how the interactions between two water molecules, not inside the water molecules. So C is the best answer. That's a tough problem. You're not going to get them all. This is my PES question. I love this question. So here's the thing. This is oxygen. What you got to know is look at your chart, and oxygen is atomic number 8, and nitrogen is atomic number 7. That's going to be important. Also, because oxygen is in group 5A, this means it has 5 valence electrons, and this has 6 valence electrons. And why that's important is because valence electrons is depth. So here's the thing. The photoelectron spectrum above show the energy required to remove a 1s electron. Now remember, there's multiple peaks. They're telling you that the only peak we're looking at is the 1s peak. The 2s and the 2p aren't here. From a nitrogen atom and from an oxygen atom, which of the following statements best accounts for the peak in the upper spectrum being to the right of the peak in the lower spectrum? Okay, guys, let's say upper spectrum, we'll say, it doesn't matter, 410 electron volts. We don't even know what an electron volt is, other than volt has something to do with energy. However, it takes like 540 electron volts to get a 1s away from oxygen. Same electron, 1s, same distance from the nucleus, first energy level. Why is it so much? Why does it take so much energy, more energy, to get an electron away from oxygen than it does from nitrogen? And what is the best thing? Nitrogen has a half-filled subshell. I get that that's true, but this is about the 1s orbital. We're not asking about the 2p orbital. There are more electron repulsion. Nope. I think you got to know this is the best answer. Smaller nuclear charge, effective nuclear charge. What is because oxygen has an effective nuclear charge of 6, pulling on the 1s electron, and nitrogen has an effective nuclear charge of 5 pulling on the electron. This pulls harder, holds it tighter, it takes more energy to knock it off. And that is PEF. This one is really confusing for me because I just had no idea where this problem was going. So it says, consider the molecules represented above, and then they go on to tell you that nonane is this formula and trifluoropentane is this formula. And look at this. They have very similar molar masses. However, nonane has a much higher boiling point, which means that it has a higher boiling point, which means it has greater intermolecular forces. Now, the thing that's crazy here is I'm looking at this problem and I'm saying to myself, this shouldn't be, because this molecule is very polar and this molecule is nonpolar, but yet this chart is telling you that nonane has more intermolecular forces. And so the question is, it says nonane and 2,3,4-trifluoropentane have almost identical molar masses, but nonane has a significant higher boiling point. Which of the following best helps explain this observation? Now this is like this observation. It's against everything I told you. This is polar, this is non-polar, this is polar. You can't see where I'm pointing. This is non-polar. This should have the higher boiling point, and it doesn't. So we have to find something that would explain that. The CF bond is easier to break. No, because when you're doing boiling point and melting point, you're not doing chemistry. When water boils, it's still water. That's all about intermolecular forces. The CF bond is more polar than the CH bond. That is absolutely positively true, except it doesn't explain. That would explain why trifluoropentane should have a higher boiling point. The carbon chain is longer in nonane. That's true. And the carbon chains are farther apart than they are in, and I don't think that's true, but basically what this is saying, when you have a really, really, really long chain like this, the intermolecular forces get crazy because it's so long and the molecules touch on so many different levels. It explains why even though trifluoropentane is polar, nonane is so much longer, and when it interacts with the other molecules, even though it's nonpolar, it's so long that they tangle, and it's hard to get them to move away from each other, if that makes sense. And so the best explanation for this seemingly ridiculous fact that nonane has a higher boiling point than 2,3,4-trifluoropentane, even though trifluoropentane is slightly polar and nonane is nonpolar, and they have the same London dispersion forces, because look at how close their molar masses are. Remember, molar mass is a function of how many electrons, but don't say molar mass, just say polarizable. And so the only thing that explains this adequately is the length of the carbon chain, and that's what it is. Okay, here's my favorite question on the whole test. I have 3 left. Okay, here's what you got to know. There are 3 half cells. Half cell 1, now remember what a half cell is. Half cell 1 is a beaker with a piece of aluminum and an aluminum solution. And half cell 2 is a beaker with a piece of copper and a solution of copper. And half cell 3 is a beaker of iron and a solution of iron. And then this chart tells you that we're going to make a battery called X, and we're going to make it by hooking up aluminum and copper. And then Y is going to be made by hooking the aluminum up to the iron. And then Z is going to be made by hooking. So this is the cell that's X, and this is the cell that's Z, and this is the cell that's Y. So first of all, I found that very confusing. Like, what is this problem asking? First question, what is the standard cell potential of galvanic cell Z? And this is almost a tricky question. This is Hess's law with one little change. Okay, we're trying to figure out this reaction. See the FES? Well, do you see an FES up here? Yep. But I have to take this equation and flip it. So 3 and divide by 3. So we have FES plus 2/3 AL plus 3. I'm not even going to do that. Here's what I need to tell you. Potential energy, cell potential has nothing to do with, it's an intensive property. It does not depend on the amount of mass present. So to get this one, I'm going to take this one. I'm going to ignore the mole ratios because mole ratio doesn't matter and because mass doesn't matter. So I'm going to flip it around. I'm going to drop the 2's and I'm going to flip it around. But when I flip it around, the cell potential goes negative. Now, the reason why we can ignore the stoichiometry is because batteries is not dependent on the mass of the battery, the mass of the electrode, because all the stuff, the reaction occurs on the phase boundary between the metal and the solution. And so it doesn't matter how much metal is inside the electrode. All that matters is the potential energy. Okay, now I need copper plus 2 to be on this side, and it's already on this side. So what I'm going to do is I'm just going to take this top one and rewrite it, dropping the stoichiometry because it doesn't matter. Now, you guys, you could carry the stoichiometry because the 2/3 and the 3/2 and all that stuff would stop. But this E, you didn't flip that around, so this is still 2. And when you do 2.00 plus negative 1.2, you get 0.78, and so the answer is B. And then when you add these together, this cancels this, and this cancels this, and you end up with FES plus CU plus 2 goes to FE plus 2 plus CU. And just for the sake of review, my people, remember, when you're working with batteries, you can, when you flip things, the sign changes, but if you double or triple or divide, you leave this alone. So that was good review. All right, in galvanic cells, X and Y, which of the following is taking place in half cell 3? So notice this. What is half cell 3? I found this so confusing. Half cell 3 is iron. So this question is asking you, in the batteries made in galvanic cell Y and galvanic cell Z, which both have half cell 3 in them, what is the iron doing? It's a very easy question right here. In galvanic cell Y, which is made by connecting aluminum and in a 1 molar aluminum solution and iron in a 1 molar iron solution, what's going on there is that in cell Y, iron is being reduced because the charge went from +2 to 0. And in galvanic cell Z, iron is going from 0 to +2. So iron is being oxidized. So what happens is in galvanic cell Y, iron is being reduced, and in galvanic cell Z, it's being oxidized. And so I believe it says reduction occurs in cell Y and oxidation occurs in cell Z. And so that's the best answer. And here's the very last. Now I did these out of order. This is, in my opinion, the hardest problem on the test because although they took off the Nernst equation, this is the Nernst equation. The E of a cell is equal to the potential energy of the cell divided by 0.0257 V ln Q. They took that off. But here's what you got to know. See this negative sign? This negative sign is important. In a galvanic cell, as you run the battery, the voltage will drop. That's why batteries run out. Now, this question is, if the half cell containing 1 molar FeNO32 in galvanic cells Y and Z is replaced with a 5 molar solution, what happens to the cell voltage? You don't have to calculate it. They just want to know if it goes up or down. Now watch this. The new cell voltage is the old cell voltage, which we know these numbers, but who cares? Okay, so let me do Y first. It's 1.22, because that's what E sub 0 is, minus, who cares, some constant that doesn't matter. It's actually 0.0257, it's some constant that doesn't matter, because the question is asking us, will the voltage go up or the voltage go down? Now, in cell phone Y, in galvanic cell Y, this gets crossed off and this gets crossed off, because pure liquids and pure solids do not go into equilibrium expression. And what's Q? Well, Q is going to be the concentration of the aluminum ion squared over the concentration of the iron ion cubed. And what they're telling you, so this would be 1.22 minus some constant times the natural log. Well, this is 1, so this is still 1. And now this has got 5, and last time I checked, 1 squared is 1. 5 squared is 125. The natural log of a number between 0 and 1 is negative, and 1/25 is between 0 and 1. And so you're going to take 122 minus a negative number. When you take 122 minus a negative number, the cell voltage actually goes up. So the first thing you got to know is in cell Y, the voltage goes up. Now, what happens in galvanic cell Z? Now I'll do the Nernst equation. The Nernst equation is not on your sheet. So the actual value you don't have to know anymore. So minus, keep in mind, minus is because you know batteries run out. It's 0.0257 volts over N. That's not important anymore. All that's important in the new thing is that you know if the voltage goes up or the voltage goes down. Okay, now in this cell, this solid and this solid aren't there. In this cell, Q is the concentration of the F ions over the concentration of the copper ions, which is 5/1. And so if you do this, 0.78 minus some constant times the ln of 5, well, the natural log of numbers bigger than 1 are positive. So this is going to be 0.78 minus some positive number, which means the cell voltage is going to drop. So basically, in cell Y, the voltage goes up. In cell Z, when you make this change, the voltage drops. So E drops. And the one that says the voltage will increase in Y and decrease in Z is C. And so without a calculator, all you got to know is how logarithms work between 0 and 1. All right, and that's it.